Hi all, welcome to the another session on quantum optics. So here we'll be discussing about higher order coherence or higher order coherence function. Okay, so in the last class we discussed about the first order coherence, and we shown that the first order coherence is able to determine the coherence length of light or its degree of its monochromaticity, but it does not give any details of statistical properties of light. So that means it cannot distinguish between the Fock state or coherent state. So it's called number state and coherent state. So there are different possible states of light quantum mechanically. So we cannot differentiate it using the first order coherence function. Okay. So we have not discussed what is by coherent state and as well as Fock state in quantum optics. So that we'll discuss later. Okay, but for the time being, you should remember there are such states available in quantum optics. So we call number state. So number state might be familiar to you because we have discussed this number state while discussing the harmonic oscillator problem in quantum mechanics and coherent state. So these are the two possible states. There are many other possible states for light, the skews light, uh, and many other states are there. Okay, now. So what we have done in the first order coherence. So in the first order coherence, we have checked the correlation of field which incident on a single detector at two different time. Okay. So in the first order coherence, we check the correlation of fields incident on a detector at two different time. It can be through the same path or different path. It need not be the same path because in Young's double slit it is through the different path. Okay. Now, apart from this, so this is actually we are finding the correlation of field. So what about the correlation of intensities? So if you have two different detectors, so how do you check its correlation? So it was done by the Hanbury, Brown, and Twiss. So it has happened in 1950. So in 1950, Hanbury, Brown, and Twiss performed an experiment. So what was that experiment? So this experiment contains light beam splitted by a beam splitter. So better keep it like this. A beam splitter divide the light into two parts. And we have detector here, two detectors. So here we have two different detectors. Detector D1, another detector D2. But these two detector, although it is at the same distance, but it detects the light at two different time. So suppose detector D1 detects at time t, and detector T2 detects the light only at t plus tau. Okay, so this tau is a time delay. So it's a variable time delay. So we can design accordingly. But however, distance from the beam splitter to D1 and beam splitter to D2 are same. So beam splitter to D1 is equal to the beam splitter to D2. The distance are same. So we can keep a box here which controls tau. Okay. And this is called coincidence counter. Okay. Now the rate at the coincidence counter, that is the both detector counts, is called the coincidence counter. So the rate of the coincidence counter C at t comma t plus tau, that obviously proportional to the intensity of the light reaches at D1 and D2. So this would be the intensity at time t and intensity at t plus tau. So now we can define the classical second order coherence function. So the classical second order coherence functions gamma 2, that would be equal to the intensity at t, intensity at t plus tau divided by the intensity at t and intensity at t plus tau, the average intensity. Now this would be the same. The average intensity at t and average intensity at t plus tau would be the same. So this would be equal to the average of intensity at t, intensity at t plus tau divided by the average intensity at t square. Now this probability, the probability of coincidence counter, usually denoted by symbol G2 t comma t plus tau. So now we have two definitions. G2 is intensity at the time t, intensity at time t plus tau. Now these are the intensity at two different counters, two different detectors. And gamma 2 is I of t f t plus tau divided by I of t square. Okay. Now this I of t and I of t plus t. So this can be written as E star at t, E star at t plus tau, E at t plus tau, E at t, all divided by E star at t, E at t square. Okay. Now the most general definition, the second order, the mutual coherence function. 2. Okay, so it need not be, the director need not be at the same distance from the beam splitter. It can be at different distance. So it can be located at different position itself. So we can denote the location of director as R1. So R1 T1 and R2 T2. Then this coincidence counter. So this will be equal to E star R1 T1, E star R2 T2 E at R2 T2 E at R1 T1 divided by average of E at R1 T1 square E at R2 T2 square. Okay, now if there is no time delay, so if there is no time delay for the measuring, then we call this a gamma 2 at tau 0. So this usually is vary from 1 to infinity. Okay, so this is called the zero time delay, the second order coherence function. Okay, now if the light incident on one detector is independent on the light incident on the other, then the gamma 2, the second order coherence function would be a constant. It will be independent on tau. Okay, so if light incident on both detectors are independent, then gamma 2 of tau would be constant. It would be independent on tau. Okay. Now, the Hanbury, Brown, and Tiss, while performing their experiment, they found that for zero time delay, so zero time delay we can call as a the simultaneous counting. So for zero time delay, detection rate is twice compared with the rate at longer time delays. Okay, the Hanbury Brown and Twist found that the gamma 2 at 0 is greater than gamma 2 at tau. Okay, so for longer time delay, the coincidence rate is lesser, and for shorter time delay, so shorter time delay means zero time delay, it is more. It is basically twice. I think better instead of greater, we can write it is twice for large tau. So what it means? So it means that for zero time delay, the photons are arriving simultaneously at the both counters. Okay, so it says that the photons must be arriving in a pair at zero time delay. But it may become independent at a longer time delays. So this implies that, or this predicts that the photons may be arriving as pairs at zero time delay, and it is independent. It is photon arrival is independent to each other at longer time delays. So at zero time delay, so there is the possibility of bunching of photons, of more number of photons are coming together. So this phenomena is called the bunching of photons. So at zero time delay, the photons are arrived as bunched pairs, and this phenomena is called photon bunching. There is its opposite effect also, the photon anti-bunching. So the photon anti-bunching happens. What is mean by photon anti-bunching? So here this gamma 2 of 0 is greater. So in such cases, the gamma 2 of 0 would be lesser than gamma 2 at some other time tau. So this is called photon anti-bunching, the opposite of the photon bunching. Now this photon bunching, this is a new phenomena. This phenomenon is also known as Hanbury Brown twist effect. So it's also known as Hanbury Brown twist effect. Okay, and another word is called photon anti-bunching. So with the in this second order coherence, we have introduced a new term to you, the photon bunching and photon anti-bunching. The photon bunching happens if the coincidence counting is more at zero time delay than the longer time delays, and photon and anti-bunching happens when it's opposite. Okay, now we can directly go to the quantum mechanical version of this second order coherence. Now, quantum mechanically, the probability of detection of photons at both the counters R1 T1 and R2 T2, this will be equal to the mod square of the final state E plus R2 T2 E plus R1 T1 I square. So this I and F are the initial and final state. This E plus is the annihilation operator corresponding to the first the field reaching at the first detector, and E plus R2 T2 is the positive frequency part or the annihilation part, which reaches at the location of the second detector at the location R2 T2. So remember, recall the photo detection is a restrictive process. So that is why we are using this annihilation operator term here. Okay, so we can have its slight modification. Okay, so the first thing is uh, the final state. There may be many possible final states, so we have to sum it over all possible final state. Sum it over all possible final states. So this becomes sum over f a plus r2 t2 e plus r1 t1 I square. Okay, now we can get two terms. The mod square is nothing but the product of complex conjugate and its original term. So that can be done here, and we can use the completeness relation of f. Then with that, we can show that this probability would be equal to I E minus R1 T1 E minus R2 T2 E plus R2 T2, then E plus R1 T1 I. Okay. Now, again, in the last video, we have discussed that the initial state I need not be pure. So initial state I need not be pure. So usually it may be in a mixed state, and mixed state the density operator has to be defined, which is sum over I Pi I. So hence what happens is the second order the quantum coherence function R1T. Okay, what we can do, we can write one more step. So therefore this P2 is simply the trace of rho E minus R1T1 E minus R2T2 E plus R2T2 E plus R1T1. Good. So this is nothing but the G2. So therefore this G2 R1T1 R2T2. You can write in two ways. One is we can write as a trace of rho E minus R1T1 E minus R2T2 E plus R2T2 E plus R1T1, what is also equal to sum over I Pi I E minus R1T1 E minus R2T2 E plus R2T2 E plus R1T1 I. Okay, so we can define the normalized second order coherence function. We shall define by symbol G2. So G2 would be equal to G2 R1T1 R2T2 all divided by G2 R1T1 G2 R2T2. Okay, so a field said to be coherent in the second order if G2 is 1. So if G of 2 equal to 1, then say that the field is coherent in second order. Now we can also see that this the complete coherence is also connected with the factorization. So if G2 R1 T1 R2 T2 equal to G2 R1 T1 into G2 R2 T2, then G of 2 would be 1. Okay, so the second order coherence is also connected with factorization. Okay, now we can express this G2 in terms of the field operators in terms of the annihilation operator. So better we can take for single mode. Can consider single mode field. So this G of 2 tau, this would be equal to the average of E minus at time t, E minus at time t plus tau, E plus at t plus tau, E plus at t. Its average will divided by E minus at t, E plus at t E minus t plus tau, E plus at t plus tau. This E plus basically represent the positive frequency term and connected with the annihilation operator, and E minus connected with the creation operator, and basically it is independent on tau. So for single mode, okay, single mode is already written there. So this become the average of A dagger, A dagger, A, A divided by A dagger, A, A dagger, A. Now this A dagger A is called number operator and by symbol N. The N is A dagger A, and the commutator A dagger equal 1. So we can rewrite this A dagger A as N, but before going to write that N, we can use a commutator here. The A dagger minus A dagger A equal 1. So A dagger A is A dagger minus 1. So therefore this become A dagger. A dagger A can be A dagger A can be written as A dagger minus 1 divided by this is number operator, this is number operator. So is average of number operator square. So this become you'll get two number operator here. So average of n square minus n divided by the average of n square. So this should be the normalized the second order coherence function, the quantum mechanical second order coherence function in terms of number operator. Okay, so if you want, we can change it slightly also. You know that the uncertainty, the square of uncertainty is the average of n square minus average n square. Okay, so this is your G2 of tau. So this would be equal to average n square minus average n divided by average n or square. So this average n square can be written as delta n square plus average n square. So this would be delta n square average plus average n square minus average n divided by the average n square, and this would be equal to 1 plus the average of delta n square minus average n divided by average n square. Good. So this is your G2 of tau. Now we can show that the for coherent state that we'll discuss later. So for coherent state, we can show that this G2 of tau equal 1. And for Fock state, Fock state is also known as number state. this G2 of tau, usually that would be 0 if number of photon is either 0 or 1, and it would be equal to 1 minus average n by n square for n greater than or equal to 2. Okay, so remember this coherent state. The coherent state is always for coherent state. The second order coherence function, the normalized second order coherence function is always 1. But for number state, this G2 of tau is not always 1. It is 0 for the if the number of photon is 0 or 1, and it depends on the value of the average number of photon for the value greater than 2. Now, what about G1 for coherent and Fock state? So for G1, G1 is a first order coherence function. So G1 is 1 for both Fock and coherent state. So again, we have not discussed what is coherent state and Fock state. That we'll discuss later. Okay, for anyhow, the point I want to make is we cannot distinguish the different state using the first order coherence function, but it is possible to distinguish the different possible states of light using the second order coherence function. So that is what I am going to highlight here. So if you look at G1, the G1 is always 1 for both Fock state and coherent state. Now these are the not only possible state. There are thermal state also, the squeezed state also. There are many other possible states for light. And this is one, just two examples. Okay, so we cannot distinguish the different possibility of states using the first order coherence function, but that is possible using second order coherence function. So that is what I'm going to highlight here. Okay, so with this discussion, we have completed about the coherence function or correlation function. Actually, both are same. We have discussed the classical coherence function and as well as the quantum mechanical coherence function up to the second order. So even its higher order term, higher order correlation is also can be defined. So this is just the extension of this. So if you look at here, so this is your G2. So this is your G2, and what was your G1? If you just recall, what was your G1? G1 at tau is simply E minus at time t and E plus at t plus tau divided by the square root of what square of, okay, better we can use the same symbol, the square root of E minus at t, E plus at t, E minus at t plus tau, E plus at t plus tau. So this is a first order normalized coherence function, the second order normalized coherence function. Okay, so in this way we can define the third order, fourth order, and so on. So it will have the implication at certain levels. Okay, so with these remarks, we are stopping it here. So we'll see with the discussion of the Fock state and coherent state in the next class. So thanks for watching. See you later. Bye.